There's an interesting phenomenon that happens to waves. When the source of the wave and the receiver are in relative motion, we have discussed waves as a perturbation in a medium that propagates in all directions. Waves have very defined wavelength and frequency. The frequency can be thought of as the number of crests that we observe per unit time, but if you as the observer move towards or away from the source of the wave, you are moving towards or away from those crests. There is a relative velocity between you and the moving crests. This will affect the frequency that you observe. Consider a sound wave and you are moving towards the source of the sound. The wave has a wavelength lambda and it is emitted at a frequency. Because you move towards the incoming crests, you will meet those crests at a faster rate, as if you were standing still. Now let's consider a source, an emitter, that is moving towards you, the observer. So the wave is emitted with a wavelength lambda of the emitter, and is propagating with the velocity v of the wave. Now, as it's propagating because the emitter is moving, then the crests of the waves are going to pile up in the direction of motion and are going to be separated away in the opposite direction. Now, the observer will measure lambda ops, the wavelength of the observer, and that wavelength is going to be the wavelength of the emitter minus the distance traveled by the emitter. Now, we can write that distance as the velocity multiplied by time, and in every oscillation, that time is going to be the period, which the period is 1 divided by the frequency. So we can write that as 1 divided by the frequency of the emitter. Now, the wavelength of the observer is just the velocity multiplied by the period, so velocity multiplied by t, and the wavelength of the emitter can be written as the velocity of the sound times the period of the emitter. Now let's rewrite, for example, now v is the velocity of the sound, and instead of the period of the observer, I will write 1 of the frequency of the observer, 1 over f sub o, and then I continue, velocity of the sound multiplied by 1 over frequency of the emitter minus the velocity of the emitter divided by the frequency of the emitter. I can rearrange the right-hand side of this equation because I can factor out 1 over f sub e, and then rearrange. I can multiply f sub e from the right to the left-hand side, and f sub o, which is divided on the left-hand side, I can put it on the right-hand side, and finally I get that the frequency measured by the observer is the frequency of the emitter multiplied by v over v minus ve, where v is the velocity of the sound and v sub e is the velocity of the source, the velocity of the emitter. Notice that because the denominator of that ratio is smaller than the numerator, we have that that's a smaller number than 1, and what we have is that the frequency measured by the observer is larger than the frequency measured by the emitter. So, which makes sense because the observer is receiving more crests per unit time that they were emitted from the emitter's reference frame. Now, we can do the opposite. We can assume that the source is going away from you, the observer, and we should get something equivalent, but in that case, we should expect that the frequency of the observer in that case is going to be smaller than the frequency of the emitter. So you can follow the same steps as I did and find that the frequency of the observer, if the source is moving away from the observer, is going to be v over v plus ve times fe, where v is the velocity of sound in the medium, v sub e is the velocity of the source of the emitter, and f sub e is the frequency measured by the emitter. Now, if the one that is moving is the observer instead of the source, then we find that the frequency of the observer moving towards the source is f sub o is equals to v plus v sub o divided by v multiplied by f sub e. And if the observer is moving away from the source, we get that the frequency measured by the observer is v minus vo divided by v times f sub e, where again v is the velocity of the sound on the medium and v sub o is the velocity of the observer. Now, all these four equations, we can just write them as a single equation. The frequency measured by the observer is V plus or minus VO divided by V minus or plus VE times FE, where the top sign indicates that the observer or the emitter is moving towards and the bottom sign is moving away from the other one.